Welcome to sinusoidal functions. Let's go. Periodic nature is key to the sinusoidal function, but what is periodic nature? Periodic nature is basically when a graph repeats itself over and over, but it has to repeat itself within a certain range, although it can have infinite domain. A graph that only goes up 1 and down to -1 over and over again is basically the same section copied and pasted for infinity, and that is periodic. Whereas, if it continuously goes up, it never actually repeats itself. Its range never repeats, the points never repeat except for the change in x. This is not periodic nature. This is not a periodic function. What is an example of periodic nature? We're going to look at the unit circle. One great example of periodic nature is the unit circle. We know that points that are coterminal have the same cosine and sine, aka the same x and y value, because they are one full rotation around since that point. So if we were to plot it, say we want to plot sine. So we're going to take the y value of every single point. So we'd start here and all of this is positive, cross here to 0, and all of this is negative. So it would look something like this, where this is the maximum sine, which would be right here, where it is 1. And then down here would be the lowest, which would be -1. And they would start at 0, 0, and it would end, if we're doing just one rotation, at 2 pi 0. But if we just continue rotating the circle, it continues for infinity. And it has periodic nature because it repeats like this for infinity. So let's talk about a sine function. It is one example of a sinusoidal function, and it is sine of x equals y. Now, what are all the parts of the sine function? This is also a parent function, so it's very important to know. The first thing to know is that it intersects the y-axis on the x-axis, right here. And it intersects it again at pi. It has a maximum y value of 1 and a negative y value of -1. And then it once again crosses at 2 pi. So what are some of the features of this graph? Well, one way to describe a wave function is by its amplitude. That is the distance between the middle, or the line that cuts straight through the middle, and one of its maximum or minimum points. And here the amplitude is equal to 1. You can also find it by finding the difference in y value between the maximum and minimum point. Since this is 1 and -1, that would be 2, and then you would divide it by 2, which gives you 1. The distance between two points that have the same y value and the same slope is 1 period. So for example, right here we have a period of 2 pi. It's not pi because these have different slopes. 0 to pi would be 1/2 period. Finally, we have its midline, which is halfway between the minimum and maximum points. The midline for a regular sine function is y equals 0. For a cosine, it's very similar. It has the exact same period, and it has the exact same midline, but it intersects the y value at its maximum, which is 1, and then looks something like this. Now, what if we transformed this function? Well, we would use a different formula to describe a transformed function. This looks pretty similar to some other transformed functions we've done, such as a parabola. Here we have a, or the vertical dilation scale factor. We have b, the horizontal dilation scale factor. Of course, that scale factor would be 1 over b because it is impacting the x value and everything's flipped that way. C is the horizontal translation value, and d is the vertical translation value. So basically, this would be dilated by a scale factor of a vertically, and then by a scale factor of 1/2 horizontally, and it would be translated with a vector of CD. C, not negative c, because it impacts the x value and thus is opposite. But these also mean different things for the graph. A is equal to the amplitude. This is interesting because normally the amplitude is 1, and so we don't have an a. And if we have, say, a equals 2, its value is the same factor that you multiply 1 by to get it, which means it is also the scale factor. B is used to find the period, and it's in a very interesting way. We know that sine of x has a period of 2 pi, and so now to get the period we want, we have to multiply what we're taking the sine of by b. And so that factor would be 2 pi over the period. We would divide 2 pi by the period to find what value we multiply 2 pi by to get our period. And this also means that 2 pi over b equals the period. And since it is on the inside, it is flipped. But that's how you find the period, and that's how you find b. Since it impacts x, x has to be greater if b is smaller to get the same y value. For example, if b is 1/2, x and it has to be twice as large, which is why everything is reversed when you do transformations within the function. And so that is why here we can solve for b, but when actually applying it, the scale factor is 1 over b. C is just the horizontal translation, but it's also called the phase shift, which means the exact same thing. D is the vertical translation, but it is also the value of the midline. Because the midline is normally 0, anything added or subtracted, and thus D would then become the midline. So this is how you would get those things from a graph, and how you could use these to find things to put on a graph. C is very interesting to find, because it's not incredibly obvious how you would do it, but there is a trick. We know where normal parent functions of sine and cosine should intersect the y-axis, if it's cosine at its peak, and if it is sine at its midline. And so say you have a cosine function, or you want to have something in a cosine function, and like it looks like this. It has its peak over here. You know that normally it should have its peak here, and so therefore the point has been translated this many units. And the same thing with sine. If you have the intersection right here, you know that it's this many units translated. Another interesting thing is that there are infinitely many valid values of c, and that's because of the periodic nature of the sine function. For example, say that c is 3. It means my point has gone 3 units to the right. Now, if I wanted to get my apparent function to align with this new graph, I could also translate it by 3 plus any number times the period. Because remember, the period is just the distance between 2 points in the exact same position on the graph. If I moved it 3 and any number of this period, any number of exact same positions, it would reach the same spot. Now, how can we convert between sine and cosine functions? Well, I'm glad you asked. We know from trigonometry that cosine of x is equal to sine of x plus pi over 2. So if we want to turn any cosine function into a sine function, all we have to do is add this translation, this horizontal translation of left by pi over 2. The reverse is true. If we're going from sine to cosine, it would be x translated to the right by pi over 2. Now let's have the example of, say, y equals 3 cosine 2x plus 1 minus 3. So here we have our amplitude is 3. Our period is going to be 2 pi over 2, or pi. We have a horizontal translation of left 1, and we have a vertical translation of down 3. So how can I turn this into a sine equation? You might think that you should just add pi over 2 right here. That would be 2 plus pi over 2. But if you try graphing this, it will not work. And that is because here we have the b distributed, even though it looks the same either way. If we expanded this, we would get 3 cosine 2x plus 2 plus pi. This is not correct. What you would need to do is you would need to expand it. 2x plus 2 minus 3. Now we will add our pi over 2. So what if I wanted to do this faster and keep it in this kind of factored form? Well, all you would need to do is you'd have to think about what number pi over 2 would become if we factored out b. Remember, here we have a period of pi because of our factor b. If we factored out 2 from b, we would get pi over 4. This is 1/4 of our period. If you think about it, up here, our period was 2 pi, and we added 1/4 of that. So the key, if you want to keep it in this form, is to add 1/4 of your period or subtract 1/4 if you're going from sine to cosine. Now let's talk about different ways to solve equations with sinusoidal functions. Here we have sine of x equals 1/2. There are a couple of ways that you could do this. The first one is you could solve it numerically. This would mean looking through a set of points, a table, finding where y is equal to 1/2, and then finding the corresponding x. This is not common, and you're probably not going to be asked to do this. You don't often have a lot of sets of points unless it's a more real-life experimental data that you're working with. Next, you can solve it graphically. And how you would do this is you would graph y equals sine of x, and you would also graph y equals 1/2. And you would see where those two lines intersect using Desmos or a TI-84 calculator or whatever graphing calculator you have. However, the way that we want to do it is we want to do it algebraically. So if we wanted to solve this by hand with nothing but like a standard calculator, how would we do that? Well, first we would isolate x. Inverse of sine of 1/2 is equal to x. The y value on the unit circle of that point with angle theta would be 1/2. Remember our unit circle, which angles have 1/2 as their sine value or as their y value? Well, that would be pi over 6. And when you think about the unit circle, you know that the first and second quadrant have sine be positive, and here we have positive 1/2. So it would also be 5 pi over 6 in the second quadrant. And so now we have our first two answers here. But there are more answers than this. These are answers between 0 and 2 pi, the first rotation of the unit circle. However, it goes on infinitely because of its periodic nature. So how can we find more answers? Well, you would simply take these two answers that you found on the first rotation and add a period to them. So since our period is pi over 2, to find our answers on the second rotation, we've gone once, now we're starting again, and we're seeing which ones have our correct sign. We would do pi over 6 plus 2 pi. And that, if we wanted to have it over 6, that would be 12 pi over 6. And so now we have another answer, which is 13 pi over 6. We would do the same for 5 pi over 6. So what you would do is you would continue adding periods to your two preliminary answers until you have gone out of bounds of the domain that they've set for you, such as between 0 and 4 pi. The key thing is to get all of the answers from the first rotation first and then start adding. What would we do if we had a transformed sine function? What if you were given this and said, find x? This is pretty complicated, so we're going to have to simplify this a little bit first. The first thing we want to do is we want to try to isolate sine of something. That is the goal, to get the function itself on one side and everything else on the other that's not sine or these parentheses. So first we divide both sides by 2. That looks a little bit better, but there is this squared right here. And if you try putting this into your graphing calculator, not Desmos is awesome, we won't know what to do with this. So we have to convert it ourselves. Sine squared is the same as sine of whatever squared. It's the whole thing squared. And so now that we have this, we can take the square root of both sides. Nice. And now that we have our function isolated and equal to something, we can now take inverse sine. Nice. Now, there is a bit of a problem with this. This isn't just x. If we found any values using our rotation method, it would be equal to 3x minus 1. So I'm going to teach you an easy way to deal with that. So there are 2 different ways that you could solve this. The first one is if you go ahead and find what equals 3x minus 1. So sine of 1 over 1/2, that would be positive. So the first 2 quadrants, that would be pi over 4 and then 3 pi over 4. So now we know that both of these individually equal 3x minus 1. And so from here, you can simplify and isolate x. So we divide these by 3, pi over 7, 3 pi over 7.
Plus x minus 1, we're going to add 1 to both sides, so pi over 7 plus 1, 3 pi over 7 plus 1 equals x.
It would just be these 2 plus that period. Let's say that our original domain was 0 to 2 pi, including both. That was in reference to x, but now we have 3x minus 1. What we need to do is do the exact same thing we've done to x onto both of these. 3 times 0 minus 1. That would be negative 3. Next, it would be 3 times 2 pi minus 1. 6 pi minus 3. And so now you have your new range for these values. And so you would go and you would add the period as normal. You would just have to stay between these 2 numbers and those would be your answers. So those are the 2 methods and they're a little bit tricky. Finally, we're going to talk about tangent. Tangent is very weird. I recently learned why it's called tangent. Here is the unit circle, and let's say we have angle theta. To find cosine, we would just find this distance. To find sine, but tangent is very weird. We would take the line that is tangent to this point, which is 1, 0, and that goes on indefinitely, and we would extend this radius until they intersected this intersection point. So now we want to have the distance between the point or the x-axis and this point of intersection, and that is tangent. But it is also sine over cosine. What if we wanted to graph the graph of tangent? It's a little bit different. So imagine that we are increasing this angle. We have it here, and tangent becomes a lot bigger. What happens when we have the angle of pi over 2 is that tangent becomes infinite because the 2 lines are parallel. And at this point, tangent is undefined. And so as theta approaches pi over 2, tangent of theta approaches positive infinity. And so, since the x of our graph, since we're graphing y equals tangent of theta, x is theta, and so at this point of theta equals pi over 2, or x equals pi over 2, tangent is undefined. This creates a vertical asymptote in our graph. And so as we come back down, tangent decreases until it comes back to 0. It then increases in this quadrant, because this quadrant is positive for tangent, and approaches positive infinity again, vertical asymptote again at 3 pi over 2 as the angle, and then it decreases again back to 0. And this creates a graph that looks like this. Oh man, that's really bad. That's really bad. These are vertical asymptotes. Here are the intersections. It repeats this infinite times. It has an infinite number of vertical asymptotes because as you keep rotating, you keep getting vertical asymptotes here and here. Let's look at the difference between 2 points in the exact same position, the 2 zeros. The angle between these is pi, and so we have a period of pi instead of 2 pi, like sine and cosine. The principal axis, or the midline, is the same. It's still d, if we were going to have a transformed version of this equation. But the key thing is that the period changes and you have these vertical asymptotes. One final problem that could happen is if you have something like this. If you wanted to solve it graphically, you'd find where these 2 functions, if you say both equal to y, intersect. But you could also solve it by dividing each side by cosine of x. You can do this because both of them have the same theta, which is x, and that equals 1. So now you have tan of x, which equals 1. And then you can solve this like I said earlier. And so that is sinusoidal functions. Thank you for watching.